right. Hello, class. I hope you're doing well. Mr. P here. Thank you, the three of you who are logged in live. Couple of updates. My Crocs arrived yesterday. I love them. Been wearing them all over the place. Very comfortable. They've got kind of like a textured. You guys see that? It's like bumpy on the inside, so it's like it scratches your foot simultaneously while you walk. Oh, hey, James and Luigi and Fu. And another thing came in the mail, which was my throwing axe. So I ordered a throwing axe because, as I mentioned, I really enjoyed going axe throwing. And yeah, so it came. You're supposed to cut the handle to length. Like, look at the handle on this thing. Like, who's going to throw an axe like this? That's crazy. So I think it also needs to be sharpened. It's not that sharp. See, I can, I'm not like cutting through pieces of paper with it. You ever see those commercials where they cut the piece of paper or a tomato or something? So yeah, now I can say, you ever see Lord of the Rings, Fellowship of the Ring, when they're all at Rivendell and they're like pledging themselves to the Fellowship, and Legolas is like, and my bow, and then the like orc guy is like, and my axe. Ah! So that's what I'm just thinking about. All right. Hello, everyone else who joined in. Maybe I will throw my axe sometime to study rotational motion. All right, well, let's get into the physics. And so I've got a 2009 E&M free response for you guys. And one thing I wanted to say is next week, about halfway through next week, we're going to switch over back to mechanics, because what usually happens is more people actually sign up for the mechanics exam than more people sign up for the mechanics exam than they do the E&M exam. And the AP exam is on the 11th, which is 2 weeks from Monday. So I'll be switching over. We'll be doing some other free response. No, I like that idea, Luigi. All right, so moving on to let's see how quickly we can get this free response done. Hopefully it's not as laborious as yesterday's free response. Okay. So, okay. I'm already looking at this and being like, this is laborious. A spherically symmetric charge distribution has a net positive charge, Q naught, distributed within a radius of r. Its electric potential is shown as a function of distance r from the center of the sphere, is given by the following. Express all algebraic answers in terms of given quantities and fundamental constants. For the following regions, indicate the direction of the electric field and derive an expression for its magnitude. Okay. So, for 1A, we want to derive an expression for its magnitude. Well, I'm going to use the fact that E is equal to minus the derivative of the potential with respect to distance. So I'm going to do minus the derivative of these things, okay? And so I can see that for little r less than big R, the derivative, it looks like, is q naught over 4 pi epsilon naught r times the quantity. Well, I got to do negative the derivative, so I'll put a negative out front. All right, times the quantity 6r over big R squared. So that constant term drops out. All right. Yeah. So what does that equal? It equals minus 3q naught r over 2 pi epsilon naught big R cubed. All right, and so that's a negative sign. So that tells me that for this region it points inward. Okay. Another way we can see that is that the potential is growing. Okay, as we go further from the center. All right, and so that means that the electric field points towards decreasing potential, so it will point towards the yeah. Okay, so for the other region, little r is greater than big R. We're going to do, again, negative the derivative, which is going to give us q naught times 4 pi, q naught over 4 pi epsilon naught r squared. The negative cancels out with the negative that's introduced from the derivative, and so we get a positive answer. So here I would say it is outward. Okay. For the following regions, derive an expression for the enclosed charge that generates the electric field in that region. All right. So what I would say is I would go to Gauss's law, which is this. Okay, and so what I would say is that this is a spherically symmetric system. So on the left-hand side, we just have E times 4 pi r squared. And then if we multiply both sides by epsilon naught, we get Q enclosed. Okay? So we got to take our E and multiply it by 4 pi r squared epsilon naught. So if I take this one and I multiply it by 4 pi r squared epsilon naught, I get for little r greater than big R, we are going to get the charge enclosed is, looks like it's going to be -6. Yeah, -6 q naught r cubed, little r cubed over big R cubed. Okay. And then for little r greater than big R, we're going to multiply this one by 4 pi epsilon naught r squared, and we just get Q enclosed equals Q naught. Okay? There we go. So part C says, is there any charge on the surface of the sphere? If there is, determine the charge and explain the reasoning. The answer is yes. So actually, as I was working this problem out, I was like sweating. I was like, oh, am I doing this wrong? Like, because I saw that something was amiss. And I was like, ooh, what am I doing this wrong? Am I misleading my students? This is horrible. But there's charge on the surface. So why do I say that? If we look at the charge enclosed evaluated at big R, if we use the top expression, we would get minus 6 Q naught. Okay? But if we look at the bottom expression, we just get that the charge enclosed is Q naught. So the amount of charge is enclosed is discontinuous when we go from just inside the sphere to just outside the sphere. And we can see that it switches from minus 6 Q naught to plus Q naught. So the change is 7 Q naught. And so that must be the charge that is carried by the surface. All right. D. It says, sketch a graph of the force that would act on a positive test charge in those regions. Positive, so we're going to use F equals QE. So it is basically, all it's asking you to do, since the charge is positive, the force is in the same direction as the electric field. Okay? So we're basically going to just graph this piecewise function. Okay? So we can see that for little r is less than big R, we have a minus electric field, so that means a negative force, that is linearly dependent on little r. So what our graph is going to look like is it's going to be minus linear. Okay. And then once we get to the outside of the sphere, we have a positive force, and it's an inverse square law kind of thing. Okay. So inverse square law looks like this. So we're going to see a discontinuity in the force. And the discontinuity in the force is a result of the charge that was on the surface. All right. Let me see if I got questions about that. Hey, Selma. It looks like Fu is disgusted that you said hello. He says you. I don't know if he's saying you because you said hello or because of the problem that we're doing. All right. E&M number 2. Boom. A 9-volt battery is connected to a rectangular bar. The electrons are the sole carriers of charge in the bar. Wires have negligible resistance. The switch in the circuit is closed at time t equals 0. Calculate the power delivered to the circuit by the battery. All right. So first thing we want to do is we got to figure out what is the resistance of the bar. And so to figure that out, I'm going to use rho L over A. So I know that the cross-sectional area is 5 times 10 to the minus 6. I know that the length is 0.08. And I know that the resistivity is 4.5 times 10 to the negative 4. All right. So let me work that out really fast. 4.5 times 10 to the negative 4 times 0.08 divided by 5 divided by 10 to the minus 6 gives us a resistance of 7.2 ohms. And then power equals V squared over R. It's a 9-volt battery, so I have 9 squared over 7.2. Which gives 11.25 watts. So that's part A. Part B, on the diagram below, indicate the direction of the electric field in the bar. So we can see that what was I going to say? We can see that the if we look at this bar, it kind of looks like this. Here's point A, here's point B. So the battery is right here, like that. So we can see that the positive terminal of the battery is connected to side A, and the negative terminal is connected to side B. So that means that side A is high potential, side B is low potential, and the electric field points from high potential to low potential. So the electric field would have to point in this direction. All right, that's the direction of the electric field. Which is what we would expect, because there's got to be an electric field, otherwise the resistance would stop the charge in the middle of the resistor. Okay. Part C, calculate the strength of the electric field in the bar. Well, electric field is minus dV dx. We can only assume that the electric field is uniform, so we're going to approximate this by change in voltage over change in X. We know that the voltage is 9 volts, and we know that the length of the resistor is 0.08 meters. Okay, so 9 divided by 0.08 is 112, 113, 113 volts per meter. D. A uniform magnetic field perpendicular to the bar is added to the region around the bar as shown below. Calculate the magnetic force on the bar. So we are going to use magnetic force on a wire is ILB. Okay, and it's perpendicular. L and B are perpendicular, so I don't have to worry about the sine theta term. The current I didn't actually calculate. We've got 9. So if I do current is V over R, we have 9 volts and 7.2 ohms. So I got 9 over 7.2. So my current is 1.25 amps. The length of the bar is 0.08, and the magnetic field is 0.25 Tesla. So that gives a force of 0.025 newtons. Part E says the electrons moving through the bar are initially deflected by an external magnetic field. On the diagram below, indicate the direction of the electric field that is created in the bar by the deflected electrons. So the question is, which way are the electrons moving? All right. So the conventional current is going this way. All right. That's the direction of the conventional current. But you have to remember that that has to do with the flow of positive charge. So that means that negative charge, the electrons, which are actually doing the motion, is in the opposite direction. So we have the velocity of the electrons is that way. All right? And then it shows that the magnetic field is in the page. So what we have to do is we have to figure out what is the force on the electrons. So I'm going to use the left-hand rule because it's an electron. Put my pointer finger in the direction of the velocity. I point my my middle finger in the direction of the magnetic field, like that. And so I can see that the force is upward. You can try it yourself. So that means that these electrons are going to get pushed upward towards the top of the wire, which means that the bottom of the wire is going to be positive. Oh my gosh, it looks like a capacitor almost. And the electric field is going to go, that's created by this charge distribution, is going to go upward from positive to negative. Part F. The electrons eventually experience no deflection and move through the bar at an average speed of bleh. Calculate the strength of the electric field indicated in part E. So this is crossed electric and magnetic fields. So we have the electrical force, QE, is equal to the magnetic force, which is QVB. All right? And so the Q's cancel out, and we get E equals VB. The velocity, it says, is 3.5 times 10 to the minus 3. And the magnetic field is 1/4 of a Tesla. So we get that the electric field is 8.8 times 10 to the minus 4 volts per meter. So notice how we actually have two electric fields. We have an electric field that's propelling the electrons through the bar, and then we have an electric field that's generated, a secondary electric field that's much smaller, that's generated by the fact that the magnetic field is deflecting electrons. Okay? Let me see if I have any questions about that. Oh, Fu says the problems are what are making him go you. Well, you know what? Learn to love the problems. I think it's fun doing problems. The reason I say that these problems are tedious is because I already know how to do them. If I was in high school, I would have loved these problems. So, all right. So let's go to question 3. We got another 2-pager on our hand. So this is CHL 423, part 2. Question 3, part A. Boom. A square conducting loop of side L contains 2 identical light bulbs, 1 and 2. There is a magnetic field directed into the page in the region inside the loop with magnitude as a function of time given by bleh. The light bulbs each have constant resistance R0, which means the total resistance in the circuit is 2 R0 because they're in series. Express all answers in terms of given quantities and fundamental constants. Derive a magnitude of the EMF generated in the loop. So first of all, we want to get the flux, which is going to be NBA sine theta, or NBA cosine theta, excuse me. But the magnetic field is perpendicular to the loop, so we don't have to worry about the cosine theta term. It's just going to be 1. And there's only one loop, so it's just N is equal to 1. So our magnetic field is AT plus B, and our area is L squared. We take the derivative of that with respect to time, negative the derivative, and that's the induced EMF, which would be minus AL squared. L squared. Only the L is squared, not the A. Part B. Determine an expression for the current through bulb 2. So current is V over R. Okay. The voltage is the voltage of the is just the induced EMF. So the voltage is AL squared. It wants the magnitude, so I'm not going to put the minus sign in there. And then the total resistance is 2 R naught. So I'm not using the resistance of the single bulb. I'm using both bulbs because the bulbs are both bulbs are influencing the current that flows in the circuit combined. Okay, part 2. What is the direction of the current through bulb 2? Well, we can see that A and B are positive constants. So what that means is that the end of the page magnetic field is increasing. So we're getting more flux into the page. And so the loop says, no, I don't want more flux into the page. I want to go back to the way it was. And so the loop is going to create its own magnetic field out of the page. And according to the right-hand rule, that would be a counterclockwise current. All right. Derive an expression for the power dissipated in bulb 1. So power is I squared R. All right. And I already calculated the current that's flowing. So it's going to be, and this is the power dissipated by one of the bulbs. So I'm going to use only one of the resistances in this expression for the R, okay? So I have AL squared over 2 R naught, that quantity squared, times R naught, because that's the current. And I get A squared L to the 4th over 4 R naught. That's the power. Okay. So now it says another identical bulb 3 is now connected in parallel with the bulb, but it is entirely outside the magnetic field as shown below. How does the brightness of the bulb compare, of bulb 1, compare to what it was in the previous circuit? All right. So what I'm going to say, so if we think about it, the induced EMF, okay, the induced EMF is going to be applied for the loop that is being threaded by the magnetic field. Okay? So what that means is that because the right-hand side of the circuit has no magnetic field, it's not going to get any induced EMF for that right loop, which means that bulb 3 is not going to get any current. Okay, so that means that bulb 1 is going to, so in other words, the resistance of bulb 3 isn't going to matter because it's the loop that it's connected to isn't having any change in flux. Okay, so what that means is that the bulb is going to maintain the same brightness. All right. Now okay. So now we have part E. And so part E says so bulb 3 is removed, a wire is connected to the midpoints of the original loop as shown below. All right, so what we're doing here, so we have something that looks like this. One, two. So what we've done here, if we look at this left loop, its flux, it's getting half the flux, okay? Which means that this left loop is getting half of the EMF. All right? But if we compare it to the full circuit, this left loop here also has half the resistance because it only contains one bulb. So also R is half. All right? So we have half the voltage and we have half the resistance. So what is that going to do to the brightness? Well, that means that the current is going to be the same, but the resistance is less. So if we look at I squared R, the current went down, but the resistance stayed the same. Or sorry, the current stayed the same, but the resistance went down. So that means that the power dissipated by that bulb went down. Okay? So it's going to be dimmer. Boom! That one took 34 minutes. Actually, I think it takes about 30 minutes to explain it because I think I spent a couple minutes in the beginning just goofing off. All right, so that's my lesson. Please, please, please ask me questions in the Discord. I would love to talk to you. Just to say hello. Just come say hello. Tell me what's going on. So that's my lesson, and I hope you have a great afternoon.